recording, and that it is now. So welcome to our third and hopefully, not hopefully, but unfortunately, final electrical class lesson sort of session thing. In this one, we're going to be going over pneumatics, and you're going to get your final assignment kind of thing done as well. So let's get right into it. The first thing we're going to do, or first thing I'm going to do, is go through my presentation. So let's go there. Oh no, my YouTube tab started opening up. Whatever will I do? Okay, let's get right into it. So, electrical, how to wire, no, go back. Okay, electrical, how to wire pressurized weapons, also known as working with pneumatics. Okay, so do you guys have any sense of what pneumatics are? Just in general, do you have an idea, or have you ever heard of it before? Yep, okay, pressurized weapons, that's relatively accurate. Okay, yeah, so pneumatics, or pneumatic systems, are essentially systems that instead of using electricity to power itself, it uses pressurized air. So that's basically what it's about. It's using pressurized air. And while you think it's separate from electric, it is controlled by electric signals because, again, a robot, or a brain, which is a roboreo, is electric. So it is controlled by electrical signals, which is why we sort of need to understand how it works. I said review and finishing motors, but then I changed my plans midway through, so we're going to come to this last. Because I realized that we can't simulate these pneumatics properly. So I'm going to explain the pneumatic stuff first, and then we're going to do the review and finishing motors thing last. But do you guys remember the CAN stuff from last time? So CAN, PWM, and the connections and motors and how to do that? Yep, okay. Okay, sounds good. So, what are pneumatics? It's a very interesting question. Pneumatics are basically, like I said, it's an air pressure system. So it's a system, a circuit on your robot that instead of using electricity to run, it uses air pressure, or pressure to air, not air pressure. So pneumatics is centralized around the concept of moving pressurized air, or using pressurized air to move parts of the robot instead of motors or other electronic parts. Pneumatic force is typically in the force of a piston, so in the form of a piston, right? So you typically have these pistons, and they only go in one direction. And the benefits are that these pistons can output force much faster, right? So air is much faster than a motor. A motor would have to charge itself up to get to that speed. A pneumatic sort of piston is just instant, like boom, and then close. And it also means that there's a lot more strength into it because air pressure loads much faster than a motor. A motor, you'd have to like sort of speed it up really fast before it gets to the point where you can sort of get a good load out of it. But air pressure, you can just instantly go like boom. It's just like a short little spasm of air. When do we use pneumatics? So like I'm saying all the stuff about pneumatics, but when do we realistically use air pressure and pistons? They can be used, or they should be used when you need a quick force in a certain direction, right? So as everyone said, they had a gearbox that shifted using pneumatics, and so that basically what I'm assuming, or how I'd assume that system works, is there's a little bit of air pressure on a piston that shifts one thing away. So it doesn't slowly move it away using a motor, it just shifts it away to the next one. Very powerful and quick force. As a question, have you guys ever worked with sort of pneumatic system before, where you sort of heard those air pumps go off and like there's a piston? Have you ever worked with those before, or is it just like just not experienced? Nope. Okay. Yeah, I mean you were in grade 9. I wouldn't assume you're there last year. You have? Okay, yeah, in a robotics team last year. Okay. That was just a segue for me to drink water. I apologize. Yeah, so pneumatic systems are actually very loud, and the reason why they're very loud are because of the multiple parts that are used in the system, and I'll get to it. And so when to use it, let me continue. So it can also be used when lifting a heavy part of the robot, or parts of the robot that are heavy and need to be moved instantly. For example, we use pneumatics to move our shooter. So a shooter was sort of like a cannon that was mounted on top of our robot. We use pneumatics to move it up and down. Last year because it's relatively heavy, and if we used a motor to do it, then we'd have to build a whole mechanism. So pneumatics are for those quick and dirty single direction movements. It can also be used to quickly move something outside of the robot, right? It depends on how competition legal it is, but a piston can be used to push boxes if needed, or a piston can even be used to lift a box once it has been collected. And so what I mean by that is, let's say you collect a box or you hug it, then a piston pops up on the bottom and just pushes that stand up. Just so that it can go that extra height. You know, again, it's really dependent on what the game needs, but pneumatics come in many different ways. So I suggest you talk with your mechanical team to sort of figure out how you're going to get pneumatics incorporated in your robot. Let's move right on. So there are several parts that are involved in our pneumatics system or our pneumatic circuit, but it all starts with our pneumatics control module, or PCM, which is also a brainstem. So you remember we have our VRM, our voltage regulator module. And so the VRM and the PCM work hand in hand. The PCM is used to control pneumatics. VRM is used to control smaller electronics and sensors. So the PCM can be considered as the brainstem, and is what will be used to control the pneumatic circuit, right? So you'll notice all these power outs, this can, and you'll notice a little unique thing over here, which is compressor out and pressure SW. Wonder if that means pressure southwest. It is also connected to the can, right? So remember, we have our can over here, and we have that complication with the software. So getting back to that software thing, what I realized was you don't need a PCM in any of your circuits. So that's not really relevant. The position of the can be anywhere it needs to go. But it's just that that circuit builder had the PCM in that position because I'm assuming that's how they built their robot. So that's just a key difference or a key blunder I made last time, which is basically you don't need a PCM or you don't need a PDP in your can wiring. But for competition, of course, you do need to connect the PDP because it's sort of a safety thing. But besides that, when you're just working around, it's not like your circuit won't work without a PDP or a PCM. It's just that for safety measures and for everything else around that, we typically do keep them connected through CAN, and we do typically keep them in certain positions. Again, you don't need to, but that's just how the simulator worked, and that's not what reflects real life. Yeah, so it is connected to CAN, and this is how it'll receive instructions from the brain itself, right? So it'll receive instructions from the RoboRio, it'll send the signals to the CAN port, and it'll be like, yo, I need you to turn on the device at port number 2. So notice how there's a little port number 2 over here. I need you to turn on that device. And so it'll head over, and it'll turn on whatever device is at P2, and something will happen, right? So the CAN is basically how our brain is going to control all of our pneumatic circuits. So everything will be connected over here. When you see VIN is basically voltage in, so this is where it'll connect to our PDP. Do you guys remember where the connectors are from the PDP to connect to the VRM or the PCM? Top area? Yeah, so it's either at like the top or the bottom. It's just that little row of pins, what's it called, Weidmuller pins. And those are the ones that connect to it. Again, didn't expect you guys to remember the name of the pins, but hopefully you guys remember the general position of where this is connected. So that's kind of where we're going to connect our pneumatics control module. Pretty cool, pretty cool. Next we have our compressor, which I deemed the bone marrow. I actually got rid of the body terms later because I realized it was a bit confusing, but it's still here, so whatever. So this is what a compressor could look like. It's used to compress air from the atmosphere and turn it into pressurized air that will be used throughout the pneumatic system. And so what that means is, obviously, we're not storing air explicitly before the match into the robot. We're actually going to use the compressor to pressurize air live. And so the way the compressor works is some advanced physics stuff, and I don't want to spend the entire, not advanced, but it's really annoying, essentially. It gathers air from the outside atmosphere, pulls it in, does some magic, and the air gets compressed, right? So lots of air in a very tight volume. It's highly pressurized too. And so if you guys have ever worked with those needle arms before, then those needle arms will actually just, not needle arms, but hydraulics, that's the name, hydraulics. So the hydraulics will essentially just, they're also run using pressure, so it's pressurized water. And so when you use that water, when you push that water, it sort of displaces something, so it forces it to move. In the same way, there's going to be, oh, I think I moved my Chrome tab. Okay, no. Okay, there we go, we're good. In the same way, there's going to be air that's basically pulled in, pressurized, and it's going to stay on the inside. And this air, it wants to move very quickly. So once it moves into some sort of an object, it's going to put a lot of force behind it, which is essentially what drives their entire system. So the compressor will, compress the air, and then it'll have to move that air somewhere. It'll have to store that air somewhere, and we'll get to that. And the compressor will also get power, so there's a motor inside that causes sort of this air to be compressed. And so this compressor motor, or what compresses the air, the electric mechanism, will be powered from the PCM. Again, it's only going to be a red and a black cable. It's just going to need power and ground, nothing else too fancy. So where it says compressor out over here, you're just going to connect your compressor power pins. And then you might wonder, what is this pressure SW for? And the pressure SW is our kill switch, or it's another kill switch. So this one is used to control the airflow, essentially. And so that doesn't do it justice, but it's basically just it's what'll allow us to turn off or on the pneumatics power that goes to the rest of it. So the compressor will remain on, but everything else just won't get pneumatics that are sent to it. So this is sort of going to be in that position where it's able to shut everything off to the circuit, but still keep the compressor running. And so this one is used to control the airflow within the circuit. It can be important because, again, if you have too much air in your compressor and for some reason your system doesn't find out, again, very rare, you can essentially tell your robot to turn on the pressure switch and it's going to release all that air nicely and gently. Again, if you release that air, just straight as it is, pressurized air, it's going to push with a lot of force outwards, and that might cause your electronics to be displaced or ruptured. So there needs to be a special mechanism that allows us to release this air, and I'll get to that as well. But this is essentially going to connect to that mechanism, and these two pins on the top also connect directly to our PCM. Right, so the red and the black. Again, the direction doesn't matter for this one, so you can technically connect it any way you want to. And it'll connect to the PCM and allow for the roborio to control if the pressure is on or off within the pneumatic system, right? So it'll control whether or not there's going to be pressurized air within the system and how that'll work. Which brings me to my next point. So where is all that pressurized air stored from the compressor? And that pressurized air will actually be stored within a tank, right? And so I didn't actually give this tank a name because this is when I stopped giving up. This is not when I stopped, but this is when I gave up on giving them names. But basically, you're going to take all your air, and and the air output is going to connect to this sort of air tank. You can have multiple of them, or you can have one, but it's important that you have enough tanks to store all the air that's going to be produced, and enough like that which you need, right? So if I'm only going to use it for one very simple use case, which is going to be, let's say, just switching the gearbox, then I don't, no, that's a very bad one, but let's say it's just for one mechanism that'll be used once or twice throughout the game, then I don't really need a lot of air. I can get by with just one tank, or even like a really small tank as well. If it's going to be something that's in constant use, or something that I will need a lot of air for, then I want more tanks, right? Because the more tanks there are, the easier it is for the air to move throughout it. So we want more tanks to store all the air that's being produced, so the compressor isn't working overtime, and that there is enough in sort of the reserves to keep the pneumatic system running. So you can consider it sort of like the battery, but it's getting charged constantly by the compressor. Yeah, okay. So everything good so far with the the PCM, the compressor, the pressure switch, and the tanks. Everything good so far? Do you guys understand those? These are the lungs. I guess you could consider it the lungs, but it doesn't generate the air. It's more just like utilizing the air. Oh, good. Oh, I see someone else has joined us. RS, is that Rahma or something? I think that's how you pronounce your name. What was the last thing you heard when you joined? All good, okay. If you heard anything. Or you might have just joined right now, in which case you've missed a decent amount. Silence. Okay. Well, just let me know once you're here, if you need some review or anything, and I can get that done. Okay, let's move on. Next, remember what I was talking about in terms of letting that air out peacefully and gently? That is our relief valve. And so the relief valve is used to release excess air from the pneumatic system, right? So let's say there's too much being generated by the compressor and the tanks are already full, then that's basically going to push air out in a lot of throughout the circuit, and that could cause something to rupture or something to disconnect. And so to prevent these disconnections, especially with high pressure within the system, we use a relief valve, and this is essentially going to get rid of the pressure in a very slow manner. And the reason why we're getting rid of it in a slow manner is basically if we get rid of it too quickly, again, it'll just sort of pump out of that one spot, right? And that's a lot of force that's going out in one direction. So if you imagine like a balloon, if we pop the balloon, that's basically releasing all the pressure inside of the balloon. So you'll notice that if you pop a balloon, or if you fill a balloon and then you stop blowing in, you let it go, it sort of like fizzles away, it flies away. There's a lot of force that's being put out in one direction. So to prevent all that force being put out in one direction, we slowly get rid of it, and getting rid of it slowly allows us to sort of minimize how much pushing and pulling there's happening within the circuit, within the system. And that's why we have our relief valves, and you can think of it as sort of a ground for the pneumatic system if you want to think of it in electrical terms. It's basically what's going to get rid of all the excess air within our system, right? So if there's too much energy, we're going to send it to the relief valve, and it's just going to get rid of it. So this relief valve is going to be connected right next to the pressure switch, because we want the pressure switch to control exactly what air will be going to our relief valve and how that works. Okay, so hope you guys are good with that. I'm going to continue on. Next, we have another fancy little thing here. It's a regulator. So the regulator should be connected right after the tanks are in a similar position to that, or right before the load. And what the regulator does is basically air comes in on one side at some random pressure. It can be higher or lower than what you need. And the regulator will make sure that it is never higher than whatever value is set previously, right? So let's say that I wanted, so pressure is measured in psi, right? And so let's say that I wanted to keep my pressure underneath 50, right? So underneath 50 psi. I think, for example, bikes are relatively or are at around that pressure. Maybe they're a bit higher. I actually don't remember. I don't have a scale for this. But essentially, say we want to keep it at 50 psi or lower. Then what the regulator is going to do is, if pressure is coming in at, let's say, 120 psi, then it's going to release whatever it doesn't need, and it's going to make sure that what exits through the other side, so the side that we want, or the output, is going to be under or equal to or under 50 psi. And so this regulator is very important, especially when you talk about pressure-sensitive components. And what I mean by pressure-sensitive components are components where if you add too much pressure, it can cause something to break. So imagine like a piston, and we pump it full of pressure, like so much pressure and force, that it just causes the piston to completely break. A piston can be considered a pressure-sensitive component, though they're typically made out of metal, so you don't really have to worry about that. But there are other things that can only handle pressure up to a certain limit, right? So if you fill up a balloon too much, it'll pop. And in the same way, we want to make sure that everything stays within the pressure limit, and that's why we use these regulators throughout the circuit. And so, yeah, I think that's a pretty good explanation. Do you guys understand relief valves and regulators? You got it. Okay, nice. I'm not tired. Who's tired? I'm not tired. Are you tired? I'm not tired. That was a joke. Okay, let's continue. So I think speaks for all. Okay, let's continue. Oh wait, I'm gonna have to pause this call very quick. Just give me a second. हाँ hello. मीटिंग में होती है हाँ okay हाँ okay yeah okay yeah bye. Okay, well, it turns out I got a phone call, but that's done and over with, so let's continue. Haha. So we've got our regulator over here. I hope you guys understand it, and let's move on. So this is going to be one of our sort of, not pressure sensitive, but this is basically what we're going to be using, or the primary use case of it, right? So this is a solenoid. This is what is primarily used when we're talking about electronics and pneumatics mixed together. And so they connect to the PCM with the red and black cables, as you see on the side of it. So you'll see that there are these two things on the side. You'll notice that this thing on the bottom looks sort of like a servo or a motor if you're experienced with those. And that's kind of similar to what it is. And so this controls a little gate on the inside, right? And so this gate on the inside will essentially control the airflow. So air will come in through this one point. And this is a double solenoid, and it's called double solenoid because air comes in through one point and it's released through 2 points. But there are also single solenoids which only have one output. We'll just take this double solenoid as our example. And so basically, we're going to send our air in through here, and these gates are going to be controlled. Now, once the gate is activated, it's going to open and allow the air to flow through. And then once it's turned off, it's going to, turn off. That's kind of how it works. And so pressure is released when the gates are open, basically, right? So when the gates open, the pressure is going to go in, it's going to come out. These gates are controlled by the roboreel, and so the roboreel will connect to the PCM, and then the PCM will and then the roboreel will send an instruction to the PCM, and then the PCM will send a signal out through these ports over here, and with the signal that goes out, it's going to turn on or off, or it's going to turn on the gates, and then it stops sending energy when the signal tells it to turn off. And so this is basically what's going to allow us to use our pressure in our system, and they're called solenoids. Does that make sense to you guys, or? Bit confusing, not so confusing, good to go, not good to go? How are you feeling? Good to go in all caps. Are you tired of the progress checks? I apologize. I just want to make sure you guys get it. Okay. Okay, and here we have the star of the show, I guess, or what most people see when they talk about a pressurized system. It's our piston. And so the piston, this is a rather large one. You can have smaller ones too. It's basically going to take all that pressurized air that is sent from the solenoid, right? So it disconnects directly to the solenoid, and then, once it's on, the air goes through. Once it's off, the air turns off, like no more air goes through. And in the same sense, once the air goes through here, it'll push that middle bar, or the bar in the middle. There's actually a bar on the inside, and it'll cause it to sort of extrude outwards. And then once air stops being sent, it's going to go back inwards, and that's basically how a piston works, right? So it's just a force in one direction, and that direction is upwards, or whatever direction your piston is facing, it's just going to be outwards from whatever that point is, or wherever that middle bar is. And so this is the primary force applier of the pneumatic system. Again, there's some other lesser known pneumatics utilizers that are not pistons, but we rarely ever use those in FRC. So pistons are typically the only thing you will be using. And yeah, that's basically it for the pneumatic sort of control system pneumatics thing. So for connecting our pneumatics modules, there are two important components that I haven't talked about yet, but I will talk about. And they're tubing and T-connectors. So tubing is essentially, it's used to transport the pressurized air throughout the pneumatic circuit, right? So we have wires to transport electrical energy in electrical circuits. We have tubing to move around pneumatics or pressurized air throughout the pneumatic circuit. And so it's a slightly flexible tube. Sometimes it's clear, sometimes it's not, but it's basically just going to have pressurized air on the inside. I think the standardized size for FRC, or what I googled, was about 1/4 inch or 1/4 inch diameter tube that will be used throughout the system. And so what a standard size means is basically when you're buying tubing, you want it to be in this size, so whatever the size is. I don't know if this one's accurate, so I won't say it, but I think it is. Actually, you want it to be within whatever that size is, right? And so the rule with pressurized air is, or the rule with pressure is basically, the smaller the space, the more pressurized it is, right? So if you have the same volume of stuff, let's say I have about, let's say I have 1 cup of water, or let's say I just have 1 cup of air, right? If I take that 1 cup of air and I put it into about a tablespoon volume, but I keep, so the same amount of air, but the size of the container is now a tablespoon, then the air is going to be a lot more pressurized. Right, so if you know you're working with a highly pressurized system, which we're not going to be working with in FRC, you're going to want to go with larger tubes so the pressure doesn't cause the tubes to burst. But these tubes are generally really good at keeping their pressure and not breaking apart. So we should be good with that. And so everything I think uses this one standardized size. Next we have our T-connectors. T-connectors are typically made out of brass, at least in FRC, because it's a relatively cheap material to get. I say relatively cheap with heavy coats, and they allow us to go out. So there are 2 outputs from it, from one point, right? So you guys, it looks something like a T, and I don't mean the drama. I mean that's a bad joke. Basically the air comes in from the bottom or one of the sides, and then it leads out through 2 outputs on the other 2 sides. And so what happens is, now that it's connecting out to 2 different outputs, it gives us 2 possible paths for the air pressure to go. Obviously, it also has some losses in the fact that the air pressure will be minimized a little bit, but that's just that's one of the trade-offs you have when you're getting 2 connections from one point. Since we're working with high pressure air, we want these not compressors, we want these T connectors to be sturdy and able to handle any level of pressure, which is why they're made out of metal, not the synthetic or I guess flexible material used to make tubing. Okay, that should be a good explanation of how we're going to connect it. So, open your simulation software or don't. The simulation software is actually a little bit different. It uses some technologies we haven't really talked about, some technologies that are a little bit different based on team to team. It uses something called a manifold to work, which is sort of similar to a solenoid, but not really. And so we actually won't be using the software because it's not going to be accurately reflective of what's here. It also crashes my computer, so I'm very scared for my life. And for that reason, we will not be using the simulator software to wire up our pneumatics. Rather, we will be using it to wire up the rest of our systems. And if you do have pneumatics, or if you will have pneumatics in the mini competition that we're going to do, we're going to find a way for you to express how you will wire that in a way that isn't inside of the simulator. We might have to make our own. I don't know, that sounds like a project for me to do later when I am sad. So we will we'll go on from there. So don't open up your simulation software yet. That might mean this meeting ends early, but I'm just going to leave you guys with a little short homework assignment, and we're going to call it a day. So I'll give you this time to work on your quote-unquote homework assignment. Before we get to our homework though, let's look at a simple circuit layout for a pneumatic circuit. So basically, it all starts from our compressor, right? So I'm not showing the electric part of this. This is just the pneumatic circuit. You guys will sort of have to, I'll explain where the electronics go here. But we start off with a compressor. So a compressor will get our air. Yeah, this will go into our air tank. Notice how the air tank has 2 outputs. So if I go all the way back over here, there's 2 outputs, so one over here and one over here. I guess not 2 outputs, 2 inputs and outputs. So the compressor will give air. The air will go inside of the air tank, but it'll also be able to flow out. And here we have our limit switch or our pressure switch, right? So you notice how if this is turned off, then the pressure will only remain between these two components. But if the pressure is, or if the switch is turned on, then it'll allow the pressure to continue flowing. And so one important thing of note, or to note here, is essentially that this top bit, or this top section of it, is going to be very high pressure. So this is about 120 psi. I don't know how accurate that is. It depends on the specifications of your compressor. But basically, this is going to be very high pressure. So if a tubing comes loose here or something, then it's going to be a highly pressurized component, which I like to call a highly pressurized weapon, which can go flying out. So be very, very, very careful when working with pneumatics. You don't want to hit people with these flying components because they can be going out at like a couple 100 kilometers per hour, and that could really hurt someone. It could even kill someone. So very, very careful with these high pressure components. Even with the low pressure ones, just be very careful with it. But definitely in this top section of high pressure components. Again, don't turn on your compressor until you've verified that all the tubing is highly connected. In the same way you don't connect the battery until everything is set up, you don't connect the compressor, you don't turn on the power until you know all the tubing works. So that's good to go. Next, we see our air release valve. So what type of connector do you think would go here to allow it to split into two different outputs? Can you guys give me a guess? What type of connector would go after the limit switch before the air release valve to allow for two outputs? What did we talk about? T, yes, T. All the drama. Yeah, we'd be using a T connector. And so the T connector allows, two other possible outputs from that one position, which is great for us. And what that means is it also sort of lowers the pressure, but that's okay because these are going to be sort of low pressure zones where we use our solenoids. So then the air will also go to our air release valve. So within the air release valve, it's going to slowly release the air, and so that's what's going to allow us to sort of ground our circuit, basically. Now, the pressure will also move downwards towards here. So remember, one thing to remember is pressure isn't always directional, especially when moving. Sometimes it can even move backwards. So, but thanks to the force of the compressor over here, and the T-switch, we know that it generally maintains a forward direction, but if it ever does go backwards, the goal is for it to be sucked up by this air release valve. Again, very, very rare for it to ever go backwards because of the force being generated by this compressor. So the compressor is forcing the air in one direction, and that direction is sort of maintained throughout. You guys can see my cursor, right? Or is my cursor not visible? Can you see my cursor? Hold up, let me go back. Okay, perfect. Yeah, so we want to make sure that it will remain in one direction, so there's nothing really to be sure of, but you should just be a little bit careful of that. Okay, after that, this T connection will connect to everything else we need in our system. So you'll notice that it goes downwards and it goes into our pressure regulator. So these pressure regulators, actually, you don't need any electronic power going to them, which makes them pretty cool. And so this means that they're not connected to the PCM. In that sense, I'm sure there's some electric ones that do connect somehow to the VRM, but we're not going to really be dealing with those. So for the pressure regulators, they're typically going to be analog, and I think analog is the word, yeah. And so they're just not going to work on, they're not going to work with most, I guess, electronics, which is good and bad news, right? So in one way, you can't make it modular, but in another way, it's good to know that it's always a physical issue if it's not working properly. Again, you could always use like a pressure sensor, or I guess these regulators do have dials on them that shows what PSI is going through. And so that's a good way to sort of keep track of what the pressure is throughout your system. Okay, once the pressure regulator is here, you'll notice that it keeps everything up to a certain limit. So we see that this one is at 60 psi or less. So you always want to keep the highest pressure items closest to that T connector. And do you guys know why we would do that? Why we would keep the highest pressure ones closest to the T connector? Yeah, that's exactly why. So as the pressure goes through over here, let's say that this is about 120. Or about 100 psi, right? So this 100 psi is going to go downwards, and then it doesn't necessarily, but it's just going to go in that direction. and it's going to head to our first pressure regulator. Now, if we keep our lowest pressure regulator on the first one, let's say 30 psi is our lowest one, if we keep the lowest one on the front, that means it's going to go from 100 psi to 30 psi. And so that means the rest of the air that comes out through the other side is going to be at 30 psi. And so that means that if this one is going to be something like 60, or if this one is going to be 50, then it won't get 50, it'll only get 30 psi. And so that's not going to go with as much power as we want, which is why we always want to make sure that there's an order to these things, because so it's sort of like a pyramid, or a reverse pyramid, I guess, where we want the highest ones on the top, and then we want it slowly decreasing, because the pressure will go down at each point. Good on you guys for figuring that out. Okay, so once we have our pressure going out over here, at our highest one, it's going to power, so again, we use a T connector over here, and the reason we use a T connector is because we also want to connect a solenoid, right? So solenoid is our primary force supplier. It's what, not primary force supplier, but it's what allows us to control the flow. So we're going to put a solenoid over here, and then from the solenoid outwards, we're going to connect, let's say, a piston or whatever thing we need, right? So the solenoid is going to go on one end of the T connector, and the other end of the T connector is going to connect to our pressure regulator, or a second one, third one, and so on and so forth. So does this sort of basic pneumatics system layout work? I mean, make sense, not work? Have we ever needed to increase pressure in a low pressure zone of the circuit? Typically circuits are planned out so that you don't really need to do that. I think a bad planning would be where you do need to increase the pressure, and there are some ways you can do that, but I don't think they're very FRC legal, so always make sure that it follows some sort of a general scheme. And one thing I didn't actually mention, which sort of contradicts this, is going to be the power of the solenoids. So that's, I guess, another point over here. And so you'll notice that the solenoids are powered using whatever connection they have. And so they're connected over here. So solenoids connect to these 0, 1, 2, 3, 4, 5, 6, 7 pins. So 8 pins over here. And the way they connect is basically there's going to be one sort of voltage over here. So you'll notice that there's this VSOL thing over here. So it's either 12 volts or 24 volts. And that's going to be the voltage of your solenoid. So some solenoids are 24 volts, some of them are 12 volts. I don't remember the specifications of the ones we have, but the point is that sometimes we do need to get a higher voltage on our solenoids. And so what that means is if we switch it to 24, then all of these pins, so all of the 0, 1, 2, 3, 4, 5, 6, 7, all of them will run at 24 volts. If we switch it to 12, all of them will run at 12 volts. And the way you switch it is by using this breaker. And so what the breaker does is basically it sort of overrides a circuit if you want it to work in a certain way. So if we want it all to run in 12, then we can run it all in 12, or we can run it all in 24. What that means is if you have a mix of solenoids, so some of them run in 24 volts and some of them run in 12 volts, then you're going to need 2 PCMs. So it's actually competition legal to have more than 1 PCM. But then you might wonder, oh wait, if we connect them using Weidmuller connections, how do I connect more PCMs to my circuit? And so that was gonna be a question to ask you guys. How do you think we can connect more PCMs to our circuit? What port on the PDP do you think we can connect more of them to? If we still need the VRM, we can't get rid of the VRM. Where do you think we can connect it to our PDP? Let me just try to pull up an image of the PDP too. And okay, here, wait. Okay, I think I got it. Give it a second to load. And that should be good. Okay. So I'm going to share this tab instead. You'll see it's loading. Give it a second. Okay, so on this PDP that I have over here, we know that we connect our PCM, our VRM, and our roboreel on these top 6 pins. So where do you think we would connect a second PCM if we want to use it in our system? Where do you think would be the best? Would it be these top pins for high load electronics? Would it be the CAN ports, which are used for communication? Would it be the battery ports, which are used to power the PDP? Or would it be these smaller ports over here? I guess there's a very obvious answer here, but it's okay, you know, sometimes you need to be obvious. What do you guys think? Yeah, the smaller ports. Perfect, yeah. So the smaller ports, actually, they look big, but you can connect any size wire inside of them just by sort of clipping them in. They're called Wago connectors, and so The smaller ports will be used for smaller electronics, and so these little slots in the middle, I remember I said you'd use breakers there, and so breakers are basically going to be what keep our circuit safe and make sure that if something is loading too much energy or something shouldn't be loading energy, it can be turned off instantly, right? So we're going to be using these smaller ports, and we need to connect a 20 amp breaker there. So I'm not expecting you guys to remember that, just to let you know, you can have more than one PCM. I think you can also have more than one VRM. And you want to make sure you connect them to the smaller ports with these with a certain type of breaker to make sure it stays safe and stays within the thing. So let's go back to our presentation. And let me just show you where the other stuff connects, which is also going to be important. So your solenoids connect over here. That's going to be where this connects. Pressure SW will connect to our pressure switch. Compressor out will connect to our compressor. CAN will connect to our CAN. Right, so whatever our CAN bus is. V in, voltage in, will connect to our PDP. And so that's basically that's all the electronic components of our pneumatic circuit. Okay. So, does the circuit make sense to you guys? Does it all seem good? Is everything okay? You guys understand pneumatics and sort of how we're going to wire this stuff? If you have any questions, you can ask them now, and I can run through them. All clear? Okay. Any other questions? Or comments, I guess? Where exactly are the smaller ports for multiple... I showed you a picture, Armand. You blind. It's right here, the smaller ports. They're the smaller ports on the PDP. Said that. I said that, right, guys? Please let me prove Armand wrong. I said that. Yeah, okay. Gosh darn it, Armand. I did. I hope. You're confusing me now. Okay. I think you guys are good with this now, which is great news. Okay, so I'm going to be ending... no, maybe I should give the instructions and then I should continue. Wait. Okay, what am I waiting for? Okay, I'm done waiting. A very low amount of patience here. Okay, so we're going to be doing our homework, quote unquote, assignment, which is more just like sort of a, are you familiar with electric, or are you familiar with this circuit simulator and how the electric systems work? And so I'll post the thing on the classroom soon, and so you have these, I guess, 15 minutes to sort of work through it. I'll just give you an assignment outline right now, and the instructions will be posted on the classroom. What are some of the dangers of making a pneumatic system? Almost everything. It's all working with pressurized air, so you want to make sure every single tube, every single fitting, everything is connected well and in a way where it won't slip easily, because if it slips, then again you have a lot of pressurized air going out with a lot of pressure, and that can hurt someone significantly. So everything has some sort of a danger attached to it, so I guess the safest part of it is the electrical part. But everything else, you should really make sure you double, triple, quadruple check, make sure that it's good to go, and only then should you ever turn it on, and turn on at a lower thing. Would you suggest sticking a screwdriver in the PCM? I would suggest sticking a screwdriver in the PCM only if you want to blow something up. Then I very much suggest that, but besides that, please don't ever stick in a screwdriver into the PCM. On a 24 volts load, not a good idea. Okay. Well, thank you, Aditya, for these enlightening questions. I think I'll just continue with giving off your homework assignment. I see you trying to solve for time here. Again, not really homework, very simple. What I want you to do is, I want you to open up your simulation software, which I guess I should do, but it's going to crash my computer. I mean, what? Crash whose computer? This is a very safe software. Good for you guys. Anyways, I'm going to be using it. We're going to be using the simulator, and I want you guys to create fully CAN connected system. So I want everything to be green. I want everything to be good. And so I want it to be basically 4 motors for the drive, right? So I guess you can consider it 1 for each wheel, though that's not how it works, but you can consider it 1 for each wheel. So I want 4 motors for the drive, 6 motors if you really want to challenge yourself, because with 6 motors your drive can move a lot faster too, which is really nice. So if you want a faster robot, I guess 6 is your sort of challenge step. I want everything to be fully connected, including your PCM, VRM. I don't want a pneumatic system, but the PCM still has to be connected for the software to work. So I would suggest you just make it, right? So 6 or 4 wheels, not wheels, motors. It can be your motor of choice, so you can use a Talon SRX along with a 775 motor, or you can use a Falcon 500, whatever you find more comfortable. And so just 6 or 4 motors, your battery, your RoboRio, your VRM PCM, and your radio. So just a very simple sort of thing there. Do you guys understand what I'm asking for? I can post a screenshot of it as well. And again, I'll be posting classroom assignments. So you want to export your circuit, and you can export it and you can save it as a .tkao file. So there's a save button in the corner. You want to click that, save as a TKO file, and you want to submit that to the Google Classroom Dropbox. So I'll just get that set up right now, and you guys can get started on working on your circuits. Does that sound good? Or are we having some issues with the simulator software? Because then I can help work that out. It's kind of what these. Oh, by the way, the recording will be done here. Hope you guys got the gist of the homework assignment. Again, thing on the classroom. And I guess in descriptions if you're not on our team. Because, you know, we got to think about people that are not on our team, Armand, in our recording sometimes. Not throwing shade. Okay. Well, yeah, so recording ending here. Hope you guys enjoyed it. This is the end of our electrical thing. Again, any questions? Discord fully available. I can totally, you know, help you out if you have any questions there. So please don't be afraid to ask for help. But yeah, I'm going to stop the recording now.